So let's now consider how we can account for the early effect with our hybrid pi model. So previously, we had seen that the output resistance associated with the early effect was R0 equals VA over ICQ, where VA was our early voltage. And so this is going to be another important equation as a parameter for our hybrid pi model. And so just for reference, if you look in the notes, this was on page 3.8 where we previously discussed this. And so this R0 is going to be our small signal transistor output resistance. And so remember, the basic thing we were describing with the early effect was that there is some dependence of our collector current on that collector emitter voltage. So in other words, our family of IV curves weren't horizontal in the forward active mode, but rather they had some finite slope. And if we extrapolated that back to our horizontal axis, then that was negative early voltage. So just sort of as a brief refresher there. So how do we actually update our small signal model? So let's start by going ahead and looking at what our model is without our early voltage. So we have these relationships. We had our R pi between the base and emitter. We have our dependent current source between our collector and the emitter. So our R0, as we sort of briefly mentioned here, is again relating the collector current to the collector emitter voltage. So what we need to do is we need to add a resistor R0 between our collector and emitter. So let's go ahead and extend this collector a little further this way. So let's do this. So here's our new collector, and then let's go ahead and extend this bottom portion here so we can connect some resistor R0 between our collector and our emitter. We also are going to need to move this IC. So now our IC is defined as the collector. Well, it's still the collector current. It's coming into this combination of R0 and GMV pi. And so what that tells us is what I sort of said a minute ago, sort of related to that family of IV curves, is now if that VCE voltage is changing, we expect to see some change in our current IC. Because of course current across this R0 is going to change as this VCE changes. And so that again is just representing this slight slope that we see in this top curve here based on our early effect. So we can also define sort of input voltage on this side. So if we have our base emitter voltage as our input, we have our VCE as our output, what we can see is that this early effect, our R0, our small signal transistor output resistance, is going to change our voltage gain. So early effect. And so other ways you'll see this written is our VA is not equal to infinity, so it's some finite number, and our R0 is also not infinity, so not infinity. What this does is this will change our voltage gain equation. And that's just if we're looking at voltage gain. Of course, we could be talking about current gain or various other types of amplifier, which we're going to look at later. But suffice it to say, obviously adding a resistor in there is going to change our relationships a little bit. And most of the time we're going to see it has the effect of reducing the gain. And so if you want to see more on that, I encourage you to look on page 385, example 6.2 in the textbook. It's essentially the same example you looked at in the previous video, but now we're considering the early effect. Of course, sometimes you might not be told explicitly neglect the early effect, but instead you'll be told VA equals infinity or R0 equals infinity. And so of course R0 would just be an open circuit here. So we remove it, and then we had our model that we had sort of before considering our early effect. And of course VA equals infinity means this extrapolation point here is all the way back at infinity such that these lines are horizontal. So again, just sort of different ways you'll see that represented. There are actually a couple other parameters that sometimes you will see in BJT models, and so these are mentioned on page 390 in the textbook. We are not going to consider them, so the circuit you see now is the most that we're going to consider. However, I'm just going to briefly draw in these other parameters just so that you're aware of them. So sometimes you will see an R mu which is a resistance between our base and collector. And so essentially what that is remember we have this base collector junction, it is reverse biased, but we do have some diffusion resistance associated with that junction still. And so typically this is going to be in the mega ohm range, and because of that, usually we just approximate it as an open circuit. The second one, and so I didn't want to get rid of all of that, the second resistor that we'll often ignore, but for completeness, we'll just go ahead and mention it here, is our base input. So our base input, let's see if I can get the right color, R sub B. And so note this is different from our base resistor in our DC circuit. This is something internal to our BJT, so this is still our base terminal here. And so I've lost this line here as well. But basically, this is the input resistance of the silicon going into our base junction. And so typically this is going to be just a few ohms. And so as we saw in the previous video, this R pi value is typically on the order of K ohms, which means that our few ohms, 10 ohms or less, is going to be pretty negligible. So again, the most we're ever going to consider is our early effect. We're not going to consider this. So let me go ahead and show explicitly. So we're not going to consider this. We're going to replace that with a short circuit. And we're not going to consider this. We're going to replace it with an open circuit.